Okay, so let's look at how we can perform optimization on this function f. So first of all, a good way to start, I guess, is something that we've seen before several times, would be to just apply gradient descent, right? Where we're trying to minimize our function with respect to the parameters that we can control. We set an initial parameter vector, let's call it x0, this is the first one that we're using. And then we'll do a loop while we improve. We'll update the x values following the gradient in our objective function, right? With some steps. But this is something that we've seen before. This is just gradient descent in order to reach the minimum of f. Of course, again, without loss of generality, we can also do this to compute the maximum of f, or at least the local optimum, right? But in our case now, when we consider black box optimization, the problem is that we cannot compute the gradient of f, or that in most cases f is even unknown, it's just a black box. So instead, let's look at a first simple approach, which would be to approximate the gradient. This is also known as empirical gradients. We'll approximate the gradient just by observing the input and output of our objective function. And we'll do this through local evaluations. Okay, and so specifically we're going to use the finite difference method from, it's a known mathematical method. We'll just apply it to our case. So by definition, the partial derivative of any function with respect to xi is the difference in the f value between the x that we are evaluating and some x prime over the delta x, over the difference in the x value, right? And of course, the derivative is this fraction as the difference between the x, delta x, approaches 0, or at 0, at the limit. Of course, this value is not well defined for non-differentiable functions, right? So, and that might be our case, and in any case, we don't know our function. So instead, what we're going to do is we're just going to use the definition of the partial derivative, but while considering that the delta x is some value above 0. In any case, we'll have to set it to be some value, some epsilon that is above 0 in order to compute the empirical gradient. But at the end of the day, it's only an approximation, right? As the epsilon is smaller, it should be a tighter approximation, and as epsilon approaches 0, it should be exactly the same. But as I said before, we will not use an epsilon that is 0, specifically as our function might not be differentiable, and we might have some noisy reading. So, but in any case, this gives us a very convenient, straightforward tool to approximate the gradient. Simply just sample several points on the boundaries or around the current point that we're trying to estimate the gradient for, and we'll just compute the delta f over delta x for those points, and that will give us the approximated gradient. How can we do that? So we have a few ways to do that, at least in one dimension. Of course, in more dimensions we can expand on this. But for the sake of simplicity, let's say that we're just trying to evaluate the partial derivative on a single dimension. Okay, so we actually have exactly a 1D approximation of the derivative. How can we do that? So we can do a backward difference, that is, we'll sample some point behind the point that we're trying to evaluate. We can do it by sampling two new points surrounding the point that we're trying to evaluate the derivative for. Or we can do what's called forward difference, where we sample the point that is above, it is larger than the point that we're trying to evaluate. Of course, the central difference, for which sample 2 points in order to evaluate the gradient of a middle point, is less biased, right? Where the backward difference is biased towards the rear and forward difference is biased toward the front. The central difference is unbiased, but it requires more samples, right? Because now we, instead of just sampling one extra sample from our function, we'll need to sample two, one at the rear and one at the front. So this is a well-known approach and it's a pretty straightforward one. However, it's not really applicable for high-dimensional optimization, right? So for instance, we would like to approximate the gradient, all of the partial derivatives of a deep neural network with 1 million parameters. Well, in that case, how many samples will we need?
1 million?
1 million, right, at least. And if you're doing the central one, right, if you're trying to do the unbiased partial derivative, you'll need even 2 million observations. And that's not practical, specifically if the samples are very costly. So instead, we'll do what we commonly do, we'll just use a stochastic approach, which we hope to be an unbiased stochastic approach, right? Something that we can collect just a few samples, but in expectancy, it will give us the same gradient. This is something that we've done often previously. Okay, so this is the main idea behind finite difference policy gradient. We'll try to evaluate the gradient of our objective function through m observations, right? Just as said, m can be lower than the number of parameters that we're trying to optimize. How do we do that? So for each one of the observations, so we use m observation at each step of when we compute the gradient, we use m observations to approximate one gradient. Then we might take a gradient descent step, and then we'll again sample m more observations to compute the gradient in the next iteration. For each one of these samples, what we do is, so say for instance we're trying to approximate the gradient for some vector x, around some vector x of assignments to our tunable parameters. At each observation, we'll set the original vector of x's, but for each one of them, we're going to add some random value, this delta value, and for each one of these parameters, this delta value is randomly sampled. It's either some epsilon, some small epsilon, or 0, we won't change it, or minus epsilon. Okay, so we'll do small perturbations for each one of these parameters, but randomly. Okay, while not fixing all of the others. So we'll randomly change each one of these values simultaneously for the entire vector. Then, for each one of these parameters, we're going to compute what they call the C value for the current iteration for plus epsilon. Okay, what does it mean? So all of these, out of all of the m observations, we're going to collect all those where the specific parameter, let's say x1, let's say we're computing the C plus epsilon value for x1. So we look at all of the observation where x1 was assigned plus epsilon. Okay, and we're going to take the mean of the outcome of all of these samples. And we'll do the same for C minus and for C0 for all, and we do it for, of course, for all of the tunable parameters. Then we'll define our gradient, or let's say each one of the partial derivatives with respect to each one of our tunable parameters n as 0 if C0 is larger than C minus epsilon or C plus epsilon, else we're going to define it as C plus epsilon minus C minus epsilon. Okay, so that will give us the direction. So this is something that is a bit similar to the case where we added an epsilon and removed an epsilon from a single parameter while setting all of the other parameters as fixed. But we're not really doing that because that will require a lot more samples. We're doing something more stochastic here, right? So C plus epsilon and C minus epsilon are not for the case where all of the others are fixed, but we're hoping that if we take the mean over them, they will be equivalent, in expectancy at least, right? This is a stochastic approach. So let's look at an example. 1 second, okay. Let's look at an example. So let's say we would like to minimize some function that takes two tunable parameters, x1 and x2. Let's say that for evaluating the gradient, we're going to draw 4 samples. Our epsilon is 1 for simplicity, right? We're going to add 1 and remove 1 randomly. And our learning step, let's say that it's 1. So the initial parameter vector at x0, let's say that it's, we just assign them 0 to both of the tunable parameters. And now you see that at each samples, we're going to randomly either add 1 for each one of the parameters, remove 1, or not change it, right? So in the first sample, for instance, we just increased both of them by epsilon. In the second one, we decreased 1 by epsilon, and the other we remained unchanged. And each one of these returns some value of the function. So now we can compute, for instance, C0 of iteration 0, or first iteration, plus epsilon for parameter number 1. So let's see. All of the relevant samples where parameter 1 was assigned a plus epsilon, you can see it here, and you can see it here, right? In 2 places. So we're going to average the outcome of these 2 samples, which is 4.5. Okay? And we'll do the same for C minus epsilon for 1 and so on, and of course 0 for our parameter 1, and we'll do the same for parameter 2. And once we have all of these values, we can easily compute the, we're not computing, we just have an estimation of the gradient around x0, our first assignment. And then, using the step size or using gradient descent, we can compute the next assignment. Okay?